Resilience is futile.
All right, 9/9 is a way to resilience. So what we're going to do today is we're going to talk about resilience. And specifically, we're going to talk about the classic imperative object-oriented programming model. I don't really have a good description of it. Maybe you guys know of one. Basically, Java, C#, C++, managing threads explicitly in your programming model, calling synchronous methods, that kind of interaction and communication between the objects in your system. So that's the model that we're going to talk about. And then we're going to talk about what are some of the pain points of that model. And hopefully we can, based on those pain points, figure out what some of the flaws of the model are. So if you can imagine you have a bunch of objects here in your system, and these are, think of these as service objects, not necessarily like entities. If you have these objects, they don't really do anything. The objects aren't really going to execute anything. They have no life. They just kind of sit there. They're just really places to store state, and they have instructions to do things. So what do you need to make these things actually come to life? You need threads. So the threads will kind of weave their way through these objects, through methods, and modify state as they go. And this is the fun part when you're dealing with threading, which is when you have a single code path that's executed concurrently by two different threads at the same time. So if you can imagine something like this is a very simple method. You have some state, A, B, C, and then you have some method that operates on that state. Well, if you want to consider how this will behave in a concurrent environment, you have to think about basically every possible interleaving of those threads through this particular method. And it might not just be 2 threads, it could be 10 threads, it could be 100 threads, right? So it's very difficult, even with a simple method like this, to kind of consider, okay, well, what is C going to equal? Well, if thread 1 goes through the first line, and then, well, maybe another thread comes in while that's executing that first line, et cetera, right? So it's very difficult to reason about how it's going to result in changing your state. And that gets even more complex when you deal with, you can imagine that there's not typically just one method that's going to operate on your state. You're going to have a bunch of methods that are going to operate on your state. So when you're considering, when you're reasoning about concurrency within a particular object and mutable state, it gets very complex and very difficult to hold in your head. Here's a good one from the Java space, and some of this stuff will be very Java-centric, but I think it kind of can be extrapolated to many languages like C#, C++, things like that. Here's one in a Java state. If you look at this, may ask the question, is this thread safe? And it's only one instruction on one line. But the answer is actually no, it's not thread safe, because the way that Java deals with longs, it's not actually going to write along in an atomic way. It writes one part of it and then the other part. So if you executed this in a multi-threaded environment, you could actually get completely unexpected results. But if you're a very experienced senior programmer, maybe he'll know this, but would you really trust your junior guys to know this kind of thing, right? Here's another one from the Java space. Adding the synchronized, little quote here, adding the synchronized keyword to Java was a mistake. It makes people think they can write multi-threaded code. And maybe you guys have something similar in the C# space or other C++ spaces. You have these large level constructs that you think, okay, it makes multi-threading and concurrency really easy. Well, in fact, nothing can make concurrency really easy, and they're just kind of illusions. And they make you feel good, but really multi-threading and concurrency is a really difficult problem if it's not architected properly. So one of the pain points here is that concurrency is really hard to reason about. If you've ever dealt with, I know I've heard about deadlocks and other things that you guys have run into, it's really hard to think about all the different cases and handle them properly. Now, if you also think about all of the constructs that are put in place that are introduced into the language to make dealing with threading easier, concurrency easier. This is, again, the Java space, but I'm sure you guys have equivalents in the C# and whatever space. All of these things we've introduced, mutexes, thread pools, barriers, double check locking, waits, notifies, all these kinds of things have been introduced to be able to manage concurrency. So you can see that it's very expensive in terms of the things that you have to know about and objects in libraries, and tools, and all these things. These are all things that you have to consider when you're dealing with concurrency. So there's another pain point, is that it's very expensive. And when I say expensive, it's expensive in terms of productivity, expensive in terms of brain cycles, just thinking about it. It's expensive in terms of lines of code dealing with it. If you want to do that. So one of the flaws of the classic thread synchronized method call model is that it's too complex. Concurrency is just too complex in the way that it manages it. So again, if we think about this modifying immutable state, these few methods, let's think about how we might go about testing this. So if you want to test this, it's really the same problem as before when you're reasoning about it. In order to test it, you have to test every possible interleaving of this code. And how can you do that? That's very difficult. Sometimes you can have test tools that will just kind of throw a ton of threads at particular code, but even that you cannot guarantee that every interleaving is exercised. I've seen tools will actually go ahead and instrument the code where there's certain kind of critical points that threads might have contention, that they'll put different weights and yields and things like that in to try and make those threads interleave in all the different possible ways. But it's a very tricky problem. So one of the other pain points is that it's hard to test. So let's think about the perfect bug. When I say the perfect bug, I mean the perfect bug in terms of you are designing a bug to cause the most possible damage, the most expense to your company and your team. So first thing you want with the perfect bug, it's got to be intermittent, right? It's got to be hard to reproduce. It's going to corrupt state such that this bug isn't just going to happen once and affect that particular transaction. It's going to leave the state in a bad way, and then sometime maybe the next day you're going to get some error with this bad state that you don't know how that state got into that way. It occurs at high load, so this might happen not in your kind of regular, usual testing. This will happen on Cyber Monday or something like that, when you have tons of users trying to use your system. Difficult to find the bug, just because concurrency, for the same reason that concurrency is hard to reason about, it's hard to figure out where these bugs exist and why they occur. And it's high risk. When you actually go in and fix the bug, let's say you figure out exactly what the problem is, are you confident when you make that fix that it's going to be correct and doesn't break anything else? Well, let's look at a concurrency bug. It kind of has all these traits, doesn't it? So they call these, the community sometimes likes to call these Heisenbugs. It's kind of funny. So we'll call them Heisenbugs. So really destructive, damaging, hard to reproduce bugs. So what are the flaws? What's the underlying flaw in the model that leads to bugs like this? Well, it's non-deterministic, right? You can't put inputs into the system in a certain predictable way and get the same inputs out. When you're dealing with concurrency, you never really know how the threads are going to be interleaved, so you can't deterministically test it. So let's talk about resilience. Sometimes the mindset when people are developing code that we want to be, obviously you want to have certain goals like quality, you want stability, you want to have good code that you can count on. One way to approach this is just, and a kind of a classic way that people approach this is they will just say, let's just be more careful. Let's take a lot of care. Let's have code reviews. Let's have let's test it thoroughly, etc. Right? Well, doing it that way doesn't really approach resilience. Resilience is not. It's not the absence of error, and in fact, those kinds of practices, although they're really important and they're good, if they're your only tool, it's almost like it's a security blanket. It's almost like a fantasy, right? When you approach it using those tools alone, it's like you're chasing the unicorn of no faults in your system, right? And I think when you talk about resilience isn't no faults in your system. It's not constructing your system in such a way that faults never occur. Resilience is the ability of your system to continue on in the presence of faults, right? It's being able to handle faults, absorb them, catch them, and continue to do your job or recover from those. So that's what resilience is about. So in the Netflix system, they had this thing going through their system that would just randomly shut down services and cause all kinds of havoc through their system. The question is, who would put something like that in the system? How did that get into their system? Well, the answer is Netflix put it in. They introduced something called Chaos Monkey that in production would go around and just randomly shut down services and cause all kinds of havoc. And the reason why they did that is Netflix really understands this idea of resilience, is that you're not going to be sure that your system can handle these kinds of faults unless you test for it, unless you actually force your system to be in a state where these things occur. And then you'll construct and you architect your system such that it will be able to handle these things. And in fact, some of the reason why they added that is because I think they were running on AWS. AWS would tend to do this at that time. It wasn't necessarily that reliable, right? So they want to make sure that they can handle that. So instead of being more careful, I think when we think about resilience, we have to think about not being afraid of faults, not trying to chase them out of town. The idea is to embrace them and treat them as like a first class consideration in your system. That's a good picture that talks about resilience. So if we think of something like a post office, let's think about, so the post office is a service, right? It provides a service to people. If I went up to the post office and let's say they had a particular fault condition of one of their trucks that had a flat tire, right? So let's imagine I go to the desk and I say, I want to ship this package, and they tell me, there's kind of two things they can do at this point. They know they have the truck has the flat tire. They can tell me what the problem is, or they can fix the truck. And in fact, the way that we tend to, with the usual model, the imperative model, is that instead of, we do kind of the worst of both. We tell the consumer that there's a problem with the truck, and we don't fix the truck, right? There's nothing that goes back and recovers and repairs the system. We just pass it on to the client, who more often than not has no recourse. They have no mechanism to fix that problem. Really what you want to do is you want to fix the truck, accept the package, and not tell them anything about it. That's resilience, right? And that's perhaps this is the kind of services that we want to write. And if a post office had that kind of service, then maybe get customers look like that. So what are the pain points here? The pain points are that our services tend to be unreliable. And an underlying flaw that perhaps leads to that is there's no mechanism for our systems to self-heal. We just pass on the errors and we don't really do anything about it. So let's think about errors. So here's our threads going through our object. And imagine you have an error that happens in this object over here. Well, what happens with that error? When I talk about an error, I mean, like, let's say you have something unpredicted, like you have a null pointer exception or a null reference exception, something like that. Never. So what that's going to do is that's going to propagate all the way down through all of these other objects who had nothing to do with that error, right? So what happens is these threads are so precious because this happens that you tend to do this defensive programming. So whenever you make this call that you think it might in any way have some kind of error, you wrap it in you catch an exception or something like that. Oftentimes there's not a whole lot you can do, but at least you don't kill your own processing, right? You can continue on. Well, this is not resilient. So what's the pain point? The errors tend to be catastrophic. They can take out entire parts of your system. And the underlying flaws is no error containment, right? Errors just kind of cascade through the system. So now let's think about how threads are managed. So we have all these service objects, and you might want to have some concurrency going on, some multiple things going on at the same time, some asynchrony or something. So what we typically do is we'll create thread pools. And typically we'll create those thread pools with this model. You'll create them in the objects themselves, right? So a thread pool, I'll have this thing, maybe I'll create a thread pool with like 4 or 5 threads. How we pick that number, I think, is largely arbitrary. Sometimes it has some bearing on the actual logic itself. Sometimes it's like, well, I think that's enough threads to really process what we want to do. But those threads are managed locally within those service objects themselves. But how would you manage these in aggregate? let's say you deploy this on a system that has, let's say you deploy it on, you test on your own system, maybe it has 4 cores, maybe you deploy it on a system with 100 cores, right? How do you manage to say, well, these thread pools don't really make sense in this context anymore. Maybe some of this stuff is CPU bound. I don't only want to use 6 threads, I want to use 100 threads because I have 100 CPUs I want to use. There's no real good way to do that unless you really build stuff into your system to have your, typically we don't. You have to put in a lot of effort to make that happen. And I think typically we don't do that. We just have hard-coded values in our thread pools, wherever they're defined, and that's just what you're stuck with. So if you think about threads running on a bunch of CPUs, here we have some tasks that are executing on those CPUs, and tasks are running in the threads. Those little arrows are in, and I try to model this as best I could, but we'll see how it goes. Those threads, those arrows indicate some kind of dependency. So this thread is now blocking on that other thread. So when that blocking occurs, really there's nothing that CPU can do anymore with that thread. So in order to ensure that that CPU is still being utilized, what you have to do is you have to have another thread, right? You have to be able to swap threads in and out so that you get that full CPU usage. What happens is you'll have these threads that are all kind of interacting and executing tasks, but typically they have this shared mutable state. You have all these locks and conditions, and there's this contention that these threads have with one another when they're operating on mutable state. Otherwise, it's not safe. If you don't control the interactions of your threads on your states, then it's not safe. So you have to do that. But there's some cost to be paid there because you have all this contention with all these threads, and in order to have your CPUs fully utilized, what do you need to do? You need to make more threads, right? So you just keep creating more and more threads to ensure that there's always some work for your CPUs to do in the CPU bound kind of problem. But that doesn't really scale that well. I mean, threads are not cheap. They're pretty expensive, actually. In Java, for example, they're like 300 kilobytes to maybe a megabyte. And in most systems, there's some kind of limitation on how many threads you can create, right? Imagine a system of concurrency where you could model 1 million users, each with their own concurrency abstraction. There's no way you could do that with threads right now, unless you have some kind of crazy system that can do that. And even so, like as you scale up these threads, there's that overhead of managing all these threads. There's a cost to that overhead. And then the other way too, so I mentioned you've implemented something, you have all these thread pools that are configured a certain way. Let's say you deployed it on a system. I mean, the way CPUs are going right now, they just have more and more cores. Let's say in a certain amount of time, you deploy a machine that has 1,000 cores. Is your system going to dynamically just adjust to that new resource? Is it going to use those resources? Is it going to use those CPUs? Probably not. So the pain points here are it makes an inefficient use of hardware resources, and it doesn't scale up. And when I say scale up, that means within a single machine, right? So a single machine with 1,000 cores, it's not going to make use of those without a lot of fiddling. So a flaw here is weak encapsulation, I would say. So it's a weak encapsulation of the concurrency model, the threading model itself. We have with these models, you have a tight coupling with the actual threads themselves, the OS threads themselves. And that's the only way you can really deal with concurrency is with those threads. And there's a cost to be paid to having that tight coupling. So let's think about scaling out now. So we talked about scaling up, let's talk about scaling up. So here's a system of objects, and these arrows indicate interactions between them. So imagine that you have this part of your system where you just want to, well, for whatever reason, maybe for performance reasons, I want to throw that on another machine. Maybe I want to throw it on 5 other machines, or so we can parallelize. Or maybe you want redundancy. Maybe you want to have this stuff running on another machine so that if the one machine goes down, this other part can cover something like that. Well, what do you need to do with this system to pull that piece out and move it to another machine? Well, you have to think about this interaction here. So this interaction previously were just method calls, right? There's certain assumptions that you could make with those method calls about the reliability, about the speed of it, things like that. Well, those assumptions don't make sense when you're dealing with a remote service anymore. Typically, I think what you would do is you have your interface when you're dealing with this other object, and now that interface, all the methods now have to implement some remote exception. Everybody now has to consider that you may have some other error regarding with that's caused by remoting, which wasn't really a possibility before. And it's not that typically it's not just one object that is going to be interacting, it's going to be a whole bunch of different objects. So you're going to have to change the nature of that interaction in a whole bunch of different places. So the pain point here is it doesn't scale out. It doesn't scale out to multiple machines really that easily. And the underlying flaw of the model is that there's too much coupling. There's coupling on the instance. You know what instance you're calling that method on. There's coupling on the location. You know that instance that you're calling is running locally within your process. And there's a coupling in time. I'm going to call the synchronous method, so you're going to have to execute right now, basically. You can't do it at some later time. I'm going to wait. So where do we go from here? So what we're going to do is we're going to introduce a model that hopefully resolves the flaws in the previous model, and then we're going to see what effect that has on the pain points that we had. So here's how we used to interact. So let's get rid of all of this, and instead let's have all of our service objects have mailboxes. And the way that these service objects are going to interact is they're going to pass messages. These are asynchronous messages. So that's it. That's the model. So let's consider what this model does. So first of all, let's think about what's not in this model. There's no threads in this model. So in your programming model, you don't talk about threads at all. You don't deal with threads. You don't worry about threads. The unit of asynchronous computation is your object and your message. An object and a message constitute one unit of asynchronous programming. Okay, that's how you tell the system, this is a chunk of execution that I want you to run. I don't care how you do it. You can run that on one thread, you can run it on 1,000 threads. It doesn't matter to me. And yet I still have that idea of asynchrony, right? I don't have to think about the threads to be able to define these asynchronous things that are going on. Because everything is asynchronous. All these messages passing between one another are asynchronous messages. And this is nice also because the real world kind of operates this way. When I go to the post office, for example, there's not a bunch of instructions there telling me how to ship my own package. I go and I tell them, here's my package, and I leave. And then they are responsible for taking ownership of that task of shipping that package. This is the way most of the world works, through this message passing mechanism. So the first thing we get rid of is we get rid of that weak encapsulation. We don't deal with EOS level threading model at all. We just define for the system the asynchrony construct. So now let's think about executing on the CPUs. Now you can imagine each of these messages and the objects. Now these objects are called actors in the system. This is an actor system. Each of these messages and objects are completely independent, right? So you can run them on any CPU in any order, it doesn't matter. So you can completely saturate your CPUs that way. And when you move on to other machines with more CPUs, because we don't speak to the underlying threading model of the system can take liberties and run things however it wants. So it will dynamically, it will linearly scale out to multiple CPUs, because all it has to do is run one thread through for each CPU, and it will just spread them out, right? So we get rid of those pain points through fixing that error, that problem in our model. We get rid of the inefficient use of hardware resources, and that scaling up problem just goes away. So we think about the scaling out problem. So again, we get rid of all this, and now we have message passing. Now what's interesting about this is that because it's kind of like a completely different approach to the problem. The previous approach was when you're dealing locally, you're going to interact one way, and when you're dealing remotely, you're going to interact another way. This model says, I'm going to deal exactly the same way, and I'm going to live with the same limitations, whether it's remote or it's local, right? So if you're passing a message locally, it's exactly the same protocol, it's exactly the same interaction mechanism as if it's remote. So we can just take this chunk of system and we can just move it off to another machine. And all we have to do is, all the system has to do And a lot of times this is just a matter of configuration, is to say that when you send something to this other actor, just send it over to that other machine instead, right? And nothing changes. Your objects, your actors have no knowledge, or they don't really care where things are running. And that gives you a lot of flexibility in terms of changing the topology of your system. So obviously great for a cloud type environment where you want to talk about something like not just scalability, but elasticity. So being able to spawn up resources and just have things enter the system and have them process things, and then when you don't need that processing, just get rid of them, right? It's very easy with that model. So the next thing we get rid of is, I don't know what we got rid of there. Something important, I'm sure. So, so it doesn't scale out. So again, that's a performance concern, right? Because running on multiple machines is going to be more performant in certain cases. And there's also a resilience concern. Being able to run on multiple machines, you have to if you want an actual resilient system. So let's think about the error problem again. This is what our threads do now with this system. There are threads there, but in the programming model, we don't think about it. But the threads that are actually executing, they never cross the boundaries of objects. They only ever run on one object at a time. So you never have that problem. If you have an error on any more, actually, let's talk about the interleaving first. So with each of these actors, it's going to process one message at a time. So there's no more interleaving. With each of your actors, you can guarantee when you're processing a message that no one's going to come in. It's not going to process another message while you're processing one message. So you can deal with all your state, and you can be sure that no one's going to mess with it underneath you, right? So all of those concurrency problems that you had before, they just kind of go away. So we get rid of that complexity, and we get rid of that non-determinism. Everything is completely deterministic. And then all of these constructs that you have to deal with, all this brain power that you had to expend to manage all of this concurrency, it just goes away. So here are the pain points that eliminates. It's no longer hard to reason about. When you're programming in this environment, it's really strange. Probably similar to like a node type environment where when you don't have to deal with concurrency anymore, it's a very strange thing to do, especially if you're used to concurrent programming, you're used to dealing with locks and conditions and all this stuff. When you don't have to deal with it, it's very odd. You know, you kind of reach for your concurrent abstractions, and then you just, well, I don't really need that anymore. Everything is a lot simpler, and but it's kind of weird at the same time. So, so those things go away. Hard to reason about, expensive, hard to test, and those high smugs too. So here's a fun one. So let's talk about bulkheading. And Titanic is kind of the classic example they give when they talk about bulkheading. And it's such a fun example because this ship ended up sinking. But they had kind of the right idea. So the idea was, we're not going to guarantee that our ship's not going to crash into anything. We expect that may happen. What we're going to do is we're going to compartmentalize the ship into these bulkheads, such that if there's a hole in one, it's not going to flood the entire ship and sink the thing. Well, they didn't really do it right in the case of Titanic, obviously, because they didn't fully extend the bulkheads all the way to the top. So what happened was, one of the bulkheads filled, it poured over the edge into the next, and then by the time it filled, like if you ever watched the movie, it filled 4 bulkheads. It was kind of, that was all she wrote, right? But this idea of bulkheading is a really important one. So again, thinking about the threads going through our actors, if we remember that cascading error that happened before with the multi-threaded example, that just doesn't happen. It's impossible in an actor system because actors the threads are initiated by the runtime. Only one actor is involved in any particular thread, so that any kind of exception, no matter what is an error, null reference exception, it doesn't matter what the error is, the runtime is going to catch that, right? And it's not going to affect any of your other actors. And it's a powerful abstraction because the runtime is managing all your threads, that it can build in these default mechanisms to be able to handle these errors and let you deal with them, as opposed to forcing you to think about how your strategy for dealing with this in a multi-threaded environment, or in the old model of doing things. So now we have error containment, and errors aren't catastrophic anymore. They're only ever going to affect one actor in your system. So again, let's think about the post office example. So we thought it was definitely a problem before that we didn't fix the truck. So now let's think about what we can do now that we have a runtime that's managing these errors that come up. Well, now what you can do is, and in kind of a modern good actor system, what you'll have is this idea of supervision. So for each one of your actors, in a lot of models, it will force this to be the case that every actor will have to have a supervisor. So you can't create an actor without giving it a parent, and that parent will be the supervisor. So if a child ever dies for whatever reason, it can throw any kind of exception or whatever, the parent is going to receive that. It's going to say, hey, one of your children died, and this is how it died. What do you want to do about it, right? And you can have all kinds of different strategies. You can develop your own strategy, or you can use default strategies. Like, okay, in that case, I want to kill off that actor and spawn another one. Or I want to, well, that error is not so bad, I'm just going to keep running. Or I can escalate it. I can die myself and send it up to my parent, right? So this supervision is built into the system. You have to consider this. And it's very resilient in that way, in that you have this now, you have this ability to fix that truck. Flat tire, supervisor says, the truck is a flat tire, okay, I can go and put somebody on fixing that. You didn't really have that before. You had the clients that were receiving those exceptions. Now you can have supervisors receiving those errors and doing something about it. So this model, this actor model, was, I believe it was developed by, or invented by a guy named Joe Armstrong in a language called Erlang. And Erlang was and still is an important language. It was developed for the telecom space, so they had to have these telecom servers or whatever, and these things had to be completely resilient. These things couldn't go down. So they wrote this language in this model, and with other kinds of interesting mechanisms of safety. And they created systems that had 9 nines reliability. And what does it mean when you talk about 9 nines reliability? 9 nines is basically the server will go down for about 300 milliseconds a year, right? Just like insane amounts of reliability that they created with this model. So this is a proven model of resiliency, and it's a really powerful one because it thinks about resilience kind of from the ground up. So their model is, they talk about let it crash. So in this model, because you have this safety of these supervisors, you know these supervisors are always going to think about and catch these errors. You don't have to think about the errors in your code. You don't have to do all this defensive programming. You don't have to put all these try catches in. Their motto is let it crash. So if there's a problem, just die. Just send the exception out. The supervisor knows how to handle it. So you can have very clean code that doesn't even really need to consider the errors that much because they're considered in another way, kind of in another location. So this is what happens. So you have a child die, and the supervisor can just bring up that child again. And if there's any kind of state problem that existed in that object, that kind of goes away. Like how many times have you had a system where a great solution was just restarting it, right? Well, that kind of applies that idea, but at an arbitrarily granular level within your system. You can restart very small parts of your system, or you can restart whole wings and sections of your system. And it can do this all automatically. And that produces very resilient systems because they can just come back up. I mean, we're really good at writing things that can run. We're not great at writing things that can run for a long time. This just kind of goes around that problem, approaches it laterally. So here's like a whole section coming down. I can just bring it back up. So now we have self-healing. And that gets rid of the unreliability pain point. So some other pros, again, it models the real world. You can do other really interesting things like when you send a message to a particular actor, you don't have to be the one that receives the answer. Whereas in a synchronous method, you make a call and you get the result, right? You can send a message to an actor and say, send the answer to that guy. And you can spawn a different actor just to be responsible for that specific transaction. So it kind of takes that whole idea of separation of concerns a level further. It's not like your class is just responsible for those types of transactions. You can have a specific instance of that class, that actor, that's going to be responsible for that specific transaction, right? So kind of a very powerful mechanism there. And again, with that, the whole let it crash philosophy, it produces much cleaner code. You don't have all these try catches and checking if conditions everywhere. So the small print, you lose all those guarantees about those synchronous method calls. When you have a synchronous method call and that method completes, you know a lot of things happen. You know that it's completed without error. You have the result. You can't. Those guarantees are lost. So now you have to deal with those in terms of an asynchronous way, right? You need to make sure you have a protocol in place. You're going to send a message out. You have to wait for that reply to do something with it. That reply may never come, right? So you need to handle that too. You can never block in an actor, generally speaking, because you're going to only have a certain amount of threads. You're not in control of this thread, right? So if you block on an actor, you're blocking basically an entire thread. If you have 4 threads running in your actor system, you like reduce your resources by 25%, right? So in general, don't block. There's you can set up separate thread pools in your actor system to be able to do blocking and things like that, but in general, blocking is a bad idea. And again, those interfaces that you're used to dealing with, you're not going to deal with interfaces anymore. You got to deal with messages, and you have to develop your protocols in those messages. You have to figure out a way you're going to define those and make sure they're followed. And then if you're dealing with libraries, for example, that already use something like thread-based state, thread locals, or I'm not sure what you guys have in C#, those don't really work in this case because you don't know what thread is going to be executed upon. So you're going to have to either use different libraries or come up with other mechanisms for solving those problems. So who's using this? A bunch of big companies are using this. I guess a big question would be, is this kind of like an academic, model that's really interesting, but nobody's really using it? WhatsApp uses it to build their entire backend. Facebook bought them for $19 billion, right? So this is real world stuff. People are betting real big money on this type of model and this technology. WhatsApp developed their backend in Erlang. Halo 4 was written in .NET actor system called Orleans, a really interesting actor system. So where can you get it? So on the JVM, none of us are on the JVM, but if you were, you can get it from these places. Akka is kind of the big one in terms of actors on the JVM. And there is Akka.NET implementation. So if you're interested in Akka on the .NET platform, that's a great place to look. Orleans, again, that's a really good one. And Node.js seems very actor-like to me. It's almost like a single actor. It uses callbacks instead of messages, but similar concepts. So I think a lot of those similar benefits about dealing with concurrency and things like that. Other languages, it's almost like all of the new languages that are coming out, no one's dealing with concurrency the same way that they did in the past. No one's dealing with threads anymore. Languages like Go and I can't remember the other ones, but they all have these higher level models of concurrency that are don't have all those same problems, but similar mechanisms with dealing with it to actors. So again, the takeaways here, consider the actor model if you're implementing something. It's a really powerful model. Consider something like Erlang, consider something like Akka for its same concurrency, its resilience kind of built in, designed into the system, and the inherent scalability. If not specifically the actor model, think about asynchronous non-blocking type of systems like Node and other things like that, which deliver a lot of the same benefits. I guess it's a matter of taste depending on what things you like in terms of implementations of these kinds of concepts. And then in general, not specific to any model or technology, just think about resilience in the way that they're thought about in these models, and that it's a first-class consideration. Don't just think about the happy path. Think about all of these things that could go wrong, and imagine building something to say that, yeah, throw anything you want at it. If I built this to withstand almost anything, it can handle all these errors. That's a nice feeling, I think, when you build something with that mindset. Any questions?
So you had a slide where under this model, that each actor essentially single threaded. Mm-hmm. I'm just trying to understand how that realistically, is each module really single-threaded, or is that something that I think I get that when we use this model, we're not really having to think about multi-threaded and much. But like behind the scenes in reality, is it essentially single-threaded, each model?
The system is not single-threaded. I think something like Node is single-threaded, like all of your business logic is single-threaded, even though all the like I/O and everything can be, a lot of threading can happen down there. But with an actor system, it's not actually single-threaded in that if you have two different actors, they can run in parallel, right?
And does the supervisor manage that?
Well, it doesn't have to be the supervisor. Like, so if I have this one actor and it's guaranteed to execute one message at a time. So it's kind of serial, I guess, in that way. But the system itself is not single-threaded. So you could have one thread can be executing that actor, and it could send a message over to another actor, which is also executing in another thread, right? So you have multi-threading going on.
But we're not thinking about that.
Yeah, but we're not thinking about the threading. And it's impossible to have that interleaving that happens, right? Because all of those messages are just processed one at a time in each particular actor, right? So it allows you, the goal is, and the philosophy, the theory is that it gives you the best of both worlds. You don't have to think about the threading, but it's actually more concurrent. Because in a system like this, these actors are not like threads. These actors are just a few bytes each, right? Because they don't actually entail any real OS threading or anything with them. They're just descriptions of work, right? So you can actually model in systems, they've modeled millions of these actors, and they're all completely concurrent, right? They can all be running at the same time with as many threads as you have available to you, right? But they're all completely safe in terms of concurrent access to state.
And another question I have is, the methodology where we say the child died, we can just respond. If the child was doing something, acting on one message, I guess it's our responsibility to do something with that in terms of putting it back on the queue or typical way that's handled.
Well, there's a lot of ways you can slice that one. The supervisor it'll get things like complete information about why it died, what message it was receiving, when it got that error. It can kind of decide, I suppose, whether or not it was a temporary error, and it can just queue up that same message again. But the other thing to understand about these actor systems is that there's certain guarantees that it provides, and there's certain limitations. I wouldn't say limitations, but there's an agreement that these actors have with one another. And one of the agreements is, I may not respond to you, right? That's something that you have to consider when you're sending these messages. So it's not just you might have died when you're processing this, that message may not get there, or the result may not have come back, right? So as long as you accept that that's the case, and there are some things that you have to do to handle those cases, right? But when you accept that, if you have a failure, you can just ignore it, right? You can just not reply. You don't have to reply to a message necessarily if something goes wrong, because you know that the guy on the other side has thought about that and has some timeout or something or some other mechanism. And when you're developing in this system, you'll be surprised how often you don't really care. You know what I mean? Like you kind of assume that when you're calling a message, you always need it to complete successfully and return, or like if you're returning something that's important. But there's a lot of times where you send a message, and if it completes, it's great. If it doesn't, it's not really that big a deal. Maybe some kind of update or other things like that. And it's kind of nice to be able to just do a best effort in certain cases and not worry about it if you can.
So if we get a child died, but in the child, we make some change to some variable or some database already. So is there anything that we can do this case? Because like we update, there were three like internal variables that it used. The child made the change to D already, and then he died. But if we make the change to D already, do we have any mechanism to change it back to the original state?
Yeah, I think the supervisor can have some access to that. I think some of the mechanisms, sometimes what they'll do is in the exception that you throw in your actor, sometimes you can just bury your state in there so that when you bring up the new one, you can initialize it or something like that. But in general, you have to think about it. Like all the mechanisms are there for you to be able to handle those cases, because obviously, have state and it might be important state. You know what I mean? The fact that it just went away isn't necessarily something that you can just ignore. But there are mechanisms in there to be able to get knowledge of that and be able to make decisions on it. But it is like it's not going to do everything for you. You have to put some logic in to handle certain situations. Yeah.
My understanding that the actor and the abstraction of the programming world is in the past we view the programming and everything is a procedure in the world. So we make procedures and make function call. And then they come up with the OOP, object-oriented programming model. Everything is objects and interaction between objects. But then the actor and I think model is along the path of the OOP, the same similar is the actor is the object.
Yeah.
But the interaction we favor, I think, interaction. It's similar to a developer team. Every developer is being an actor, and they interact and sending emails, and then we endlessly work about the content.
Yeah. Yeah, I think it really models well to real world things like that. And a lot of the times for modeling this stuff, you think about them in terms of real world interactions. It makes them a lot easier to understand. And sometimes just inherently they're easier to understand because you're modeling them that way, I found. Yeah. But I think I read somewhere that there was some guy, I'm not sure if it's the guy that initially talked about object orientation, but I think I read somewhere that this idea of having actors was more in line with what he actually intended when he talked about object orientation. Not just having them have the state and the behavior, but actually their own life cycles and execution paths, right? That's more kind of the next level, I think, of object orientation. Because these threads just kind of like, they're pervasive. They just kind of get through everything. They kind of break all of the things all of that encapsulation and structure that you try and set up, because they just kind of weave their way and carry state through everything and errors back through. You don't have that separation that you have with this model. All right. Thanks, everybody.
I have confidence with it. You want to try? I think I have one other slide.